Welcome back. We're going to look at properties of logarithms today. So you might recall that in our last lesson, we worked extensively with changing between logarithmic and exponential forms. Today's lessons will concentrate on using these 5 logarithmic properties. Property 1, the logarithm of 1 is always 0 regardless of the base. Property 2, when the base matches the argument, the logarithm is equal to 1. Property 3, if you have a product in the argument, we can break that into a sum of logarithms. Property 4, a quotient in the argument becomes the difference between 2 logarithms. Note that it's log x minus log y, where x is the numerator. And lastly, if we have a power, this is the same as n being the coefficient out front of the log x. Okay, so we're going to practice using those properties now within some examples. So here we go. We have a base of 2. The argument is xy over z squared. So the first thing that we can do here is use property number 4 to separate this into a difference. So that would look like this. We're going to have the log of xy minus the log of z squared. And of course, the base remains 2. From there, I can use property 3 here to make this a sum of logarithms. So this then becomes the log of x plus the log of y. So again, the product becomes the sum. That's property 3. And lastly, for this term here at the end, we can use the final property. So the 2, which is the exponent, comes forward and becomes the coefficient. And this is now equivalent to the original. Here's a second one. First, it's going to be important to remove the radical sign here. We need to keep in mind the exponent under here would be a 1. So this becomes y to the 1 over 3. This is over 7. Okay, so that's our first step. From there, we're going to use property 4 because we do have a quotient. So this will become the log of y to the 1/3 minus the log of 7. Of course, the base is 3 for each logarithm. Lastly, the exponent here can be brought forward using property 5. And we'll get our final result, 1/3 log y minus log 7. Okay, the next 2 examples have us reversing the process. So our goal will be to combine the logarithms. So we'll take a look at this one. We can rearrange this first one so that the positive term is first, like this. So log v minus log r. The base, of course, is 8 for each logarithm. We now have a difference, and we can use property 4 So we will be combining now into a quotient. So V over R will be the correct argument. And one more like this. It's important to note that before we use properties 3 or 4, we have to move these coefficients. So this then becomes a to the half. And here, 5 squared. Now that the coefficients are out of the way, we can use property 4 to write this as a to the 1/2 over 5 squared. And of course, from there, we can write square root of a over 25 as the correct argument. Now remember that when there is no index written here, it's assumed to be a 2 as required. And when there is no exponent written here, it is assumed to be a 1 as required. Okay? In general, the relationship is this. Okay? So the numerator of the fractional exponent goes here. The denominator of the fractional exponent is the index, like that. Okay, let's continue with our examples. The next examples are going to actually allow us to get a numeric answer. So what we'll do first, since we have a quotient, this becomes a difference like that. Now, remember property 1. The log of 1, regardless of the base, is 0. So here we have 0. Now, to evaluate this portion, if the base is 3, we'd like to write 81 as a power of 3. 81 is 3 to the power of 4. You can confirm that with your calculator. That's important because now we can bring the 4 forward like this. So the exponent is the coefficient. That's property 5. And what is this equal to? The base matches the argument. So if you look, that's property 2. So the value there is 1. So we end up here with 0 minus 4 times 1, which means our answer is -4. Let's try this one. The base is 6. The argument is the cube root of 6. First, eliminate the radical. This is 6 to the 1 over 3. Again, the implied exponent right here is 1. So that's where the numerator of 1 comes from. Bring that exponent forward as the multiplier. And now the base matches the argument. This is 1/3 times 1. So the answer to number 6 is 1/3. Okay, one more like this. First step, eliminate the radical. This is 25 to the 1/3. Again, implied right here is a 1. Now, the base here, however, is 5, not 25. So it would be nice to instead move to a base of 5. This can easily be accomplished because we know that 25 is 5 squared. So 25 becomes 5 squared. This exponent of 1/3 is still here. Applying the rules of our exponents means that we multiply 2 by 1/3 to get 2/3. Now the 2/3 comes forward. Property number 5 allows us to do this. Here, the base matches the argument, so we have an answer of 2/3 times 1, or 2/3. Okay, I hope that you followed those 3 examples okay. Now, for our next examples, we're going to look at questions that ask us to solve for y. So our strategy will be write each side as a single logarithm with the same base. Here we have a single logarithm. On the right, if I want to combine these, it may be easier to write the positive one first. Like this. Then remember, the coefficients have to be out of the way before you combine. We now have x plus 1 squared. The coefficient became the exponent. Subtraction allows us to now write this with 7 over x plus 1 all squared, like this. Now we have the left is a single logarithm of base 3. And the right is also a single logarithm of base 3. And since it's an equation, we can now equate the arguments. So our conclusion is y is equal to 7 over x plus 1 all squared. Okay, and we could not equate the arguments until we had a single logarithm on that right side. Okay, let's try this one. Now this time, the term containing y is not isolated, so I may want to start by isolating that term. So I'll bring that to the right and this to the left. So I'm going to subtract the log of 27. When this goes to the right, it's going to be positive. Like that. Now, I'm going to move the coefficients. This will be x to the 4. And similarly here, y cubed. With those coefficients out of the way, these logarithms can be combined. It will have x to the 4 on top of 27. And now here it is. Both sides are single logarithms with the same base. It's an equation, so I can now equate these arguments. Meaning I can write y cubed is equal to x to the 4 over 27. We're meant to solve for y, and I can do that simply by taking the cube root of the right side. Now, the cube root of 27 is 3. So I can change to this notation. If you recognize that this can be reduced further, then I urge you to reduce it further. It would be x times the cube root of x over 3. However, I was totally fine with you also stopping right here for your final answer. So right here is fine. If you again realize that since this exponent is greater than this index, we can remove x, leaving just the cube root of x here, then that's great. But you can also stop right here, okay? And I would be sure to give you full marks. Okay, so once we have a single logarithm on each side, that is the point at which we equate the two arguments, and then make sure we solve for y. So go from y cubed to y like that. Okay, one last example for this video. The difference in this example should be obvious right here. We don't have a logarithm of base 4. If you look back at our other problems, they started with all logarithms of the same base. We can fix that by inserting right here a logarithm of base 4 that would have a value of 1 only, so that it wouldn't change the fact that the right side is equal to 2. So we change it to 2 times the logarithm of 4 with base 4, because we know that this has a value of 1 according to property number 2. So we change 2 into 2 times 1. Okay, and that is helpful because now we have all logarithms. Let's move the coefficients. This is a coefficient of pi. Pi is just a number. So we begin by making it x with an exponent of pi. Similarly, now here, this becomes 4 with an exponent of 2. Remember, we're trying to solve for y, so it might be wise to isolate this term now. However, we could combine these logarithms instead and solve for y later. So we always have a couple of different possibilities. But again, we could maybe isolate this logarithm if we use subtraction here. Okay, so bringing this term to the right side means subtracting it. Now let's combine these two logarithms with base 4. It's subtraction, so it'll be 4 squared, of course that's 16, over x to the pi. And now we're at the point of the solution where we simply say the argument on the left is equal to the argument on the right. So y is 4 squared over x to the pi, or 16 over x to the pi.